Hello, everyone. My name is Karan Patel, and I'm a master's student from the University of Tennessee, Knoxville. And this is my first time here at a conference, so thank you all for having me. Today, I'll be talking about the impact of noisy input on evolved spiking neural networks for neuromorphic systems. What? Okay. I would first like to talk about some of the key benefits of spiking neural networks. The first one being that it more closely models the human brain compared to traditional ANNs. The second being that it generally produces smaller network sizes, which has the added benefit of improved interpretability. And third, it's great for low power applications, again, due to their smaller network sizes and temporal nature, which makes them ideal for on-the-edge applications and systems. And finally, the focus of this presentation, resiliency. Why isn't it? Okay, here we go. So why is noise resiliency important? Well, obviously, we want our networks to be robust enough to handle noisy input to improve our classification and control task accuracies. But more importantly, we want them to work well on specialized hardware. With the death of Moore's law, we're transitioning from traditional von Neumann architectures to more specialized systems, a popular direction being neuromorphic, which is better capable of leveraging SNN's inherent properties. However, these systems utilize novel devices such as memristors, spintronics, ferroelectric devices that are more prone to hardware noise and failures. Therefore, having a robust network is extremely crucial in helping to combat these issues. So for this work, we utilized the Reduced Instruction Spiking Processor, or RISP, which is a simplified model of a spiking processor. RISP implements integrate and fire neurons with neurons containing a threshold parameter and whether or not they will leak, while synapses have both a wait and delay parameter. Neurons also contain an action potential that can either increase or decrease based on incoming spikes, and this is processed in discrete time steps. For this work, we have weights between -1 to 1, threshold between 0 to 1, and a max synaptic delay of 5. Also, here's a RISP variant called microcaspian that our lab works with. So for a training approach, we leveraged evolutionary optimization for neuromorphic systems, or EONs. EONs optimizes the number of neurons and synapses and other parameters through evolution. It first begins with an initial population with the appropriate number of input and output neurons with a randomly initialized number of hidden neurons and synapses. Afterwards, we evaluate and rank these various networks based on their performance on a given task. The next step is then the selection and reproduction of the top performing networks to produce the children networks. We utilize tournament selection along with crossover and mutation to do this. Finally, this is then repeated for a given number of generations, with the best performing individual in the last generation being our solution. So now moving on to the data sets and applications we focused on in this study. For our classification tasks, we utilized the popular data sets from scikit-learn, including iris, swine, and breast cancer, with the following number of data instances, features, and outputs. For our control tasks, we leveraged OpenAI GYM's Carpole v1 and Lunar Lander v2. The carpole task attempts to balance a pole upright by moving the cart either left or right, while Lunar Lander attempts to land a rover on a designated area by firing either the left, middle, or right thrusters, or doing nothing. We purposefully utilize these simple data sets and control apps due to their popularity within the field, which provides a strong baseline of understanding regarding the performance of our implementations. So moving on to the experimental setup, we first gathered a baseline by training networks, first without noise injection, with 200 epochs and 20 runs each. Afterwards, we trained networks with noise injection by introducing a Gaussian distribution with a mu value of 0 and sigma calculated as the absolute difference between the minimum and maximum values of the training data times some alpha value, where alpha is cycled through these possible values shown here. The smaller the alpha value, the less noise being injected, and vice versa. After the training phase, we move on to the testing phase, where for every single network, we test with various degrees of testing noise. Again, this is denoted by the alpha values, and we also perform 20 runs of this as well. So in the end, we have every possible combination of training and testing noise for every single data set and control application. Additionally, we'll also form the same training and testing procedures for various other popular classification models within scikit-learn in order to gauge the performance of SNNs in relation to traditional machine learning approaches. We explored nearest neighbors, linear SVMs, decision trees, and neural nets with default parameters within scikit-learn and the relevant parameters shown here on the table. We also assumed that for the neural net implementation, that it is a good representation of how SNNs would perform with a backpropagation-like algorithm. It is also worth mentioning that hyperparameter tuning is a crucial step within the training phase, and we plan to further explore this aspect in relation to the resiliency of networks. However, for this work, we didn't have enough time to dive too deep into this aspect, but we found interesting results nonetheless. So here we have the results on the performance of SNNs while in the presence of both training and testing noise for the classification data sets. As you can see, the x-axis corresponds to the testing noise levels, and this is denoted by the alpha values I mentioned earlier, while the y-axis corresponds to the testing accuracies from 0 to 1. Also, the various lines depicted within the legend correspond to the training noise values. From these graphs, we can see that networks trained with noise perform significantly better while in the presence of testing noise. And this is most prominently seen within the wine and breast cancer data sets shown here. So the blue line corresponds to networks trained without noise, and we can see that testing accuracy drastically decreases as more testing noise is introduced to the system. However, networks trained with noise perform significantly better, even if they are trained on relatively low amounts of noise, as shown by the orange and green lines here, which have alpha values of 0.01 and 0.05 respectively. So moving on, here we have the results for the control tasks. Again, the x-axis corresponds to the testing noise values. And you may notice that we utilize smaller alpha values, and this was to obtain reasonable results within 200 epochs. Also, the y-axis corresponds to the fitness scores. And it's worth mentioning that the fitness scores that we achieved aren't necessarily the best possible fitness scores for these given tests, but our goal was to demonstrate the difference in performance while in the presence of noise, not necessarily produce the best performing networks. Having said that, we can see that for the carpool tasks, networks trained with noise perform worse in most cases compared to networks trained without, but they're more consistent. However, for lunar lander, networks trained with any amounts of noise perform significantly better while in the presence of testing noise. And this disparity may be due to the less complex nature of the carpool problem and its resulting networks, and the amount of noise that we may have injected to that system may have been overwhelming for it. It's hard to say for sure, and we plan to further explore this aspect in the future. Additionally, here are the results for the various classifiers, including SNNs. Again, the various lines depicted within the legends correspond to the various classifiers that we explored. It is also worth mentioning that the nearest neighbors and linear classifiers heavily rely on spatial relationships between data points. Therefore, it is expected that they'll be more resilient to the type of noise that we injected. Having said that, we can see that SNNs, shown by the purple line, still perform fairly well for both the iris and wine data sets, but they perform the worst for the breast cancer data sets for most cases. This demonstrates that although SNNs have good noise tolerance, this aspect isn't necessarily always applicable in all situations and applications. So in order to further compare the various classifiers, we utilized an area under the curve metric to determine the optimum training noise value for each of the classifiers, and we compiled them to get the best performing classifiers for every single data set shown here. As you can see, SNNs are consistently third best performing for most cases, right behind nearest neighbors and linear SVMs for the reasons I had mentioned before. Regardless, though, SNNs still outperform traditional neural networks trained in the same manner while also in the presence of testing noise, as shown by the red lines here. So in conclusion, the key takeaways are, although SNNs are believed to be noise resistant, this property isn't necessarily always true or applicable in every single data set or application or scenario. And we also demonstrated that SNNs trained with noise outperform or perform significantly better while in the presence of testing noise. And we also demonstrated that SNNs trained in this manner typically outperform traditional neural networks while also in the presence of testing noise. In the future, we plan to further explore the impact of hyperparameter tuning in relation to the resiliency of networks, while also exploring the various encoding mechanisms and how they would impact the robustness. Currently, we're exploring real-life applications that suffer from noisy sensor readings and would benefit from more resilient networks. And one such example of this is a radiation detection application that we are currently working on with Oak Ridge National Labs. So that is all. Thank you all for your time. Are there any questions?